In this recording, we're going to talk about the proof of Rolle theorem and its application. Rolle theorem is stated as follows. Okay, it has three conditions. Okay, so of course, f is a function. Okay, f is a function, and this function satisfies three conditions. Okay, three premises. It satisfies the following three premises. Number one, f is continuous. F is continuous on, F is continuous on the closed interval. Continuous on a closed interval AB. Okay. In the textbook, it says on the closed interval. It just wants to emphasize that the interval must be closed. If the interval is closed, then we can apply extreme value theorem, intermediate value theorem. So all of the properties about continuous function on a closed interval can be applied. But here, for sure, because the way we write it, we write the interval as a closed interval, and we don't have to keep the words close. Okay, it is continuous on the closed interval. Number two is that f is differentiable. In the open interval, AB. Do we have to write the open interval? We don't have to, okay? So you can even remove the interval because these are intervals. These are intervals. So these are just shorthand notation. Number three, third condition is that f of x at the endpoints, f of A is the same as f of B. Okay, there are three conditions. So under these three conditions and the conclusion is there exists a number C, okay? And we have to tell where C is. C is in the interval A, B, inside the interval, such that the derivative of the function at C is 0. Okay, so that is a Rolle theorem. Now, first, let's explain what it means, right? What it means. There are three possible cases. There are three possible cases in the proof. So when we observe the function at the endpoints, right? It could be, say, let's establish a rectangular system, right? It's a function, right? So that function takes input, produces output. The output is f of x, right? And you can see the C, A, B, these are from the input. And f of x are the output. And there's a derivative, right? So we need to understand these differences. Inputs are the categories of A, B, and all the numbers between A and B, and C is in A, B. All of these are input category. And the output category, of course, is f of A, f of B, right? That's output, okay? And f of C, of course, is also output. All right, so now let's do the proof. Okay, let's do the proof. To prove this theorem, we will consider three cases. Three cases. There only could be these three cases. The first case is one, okay, that f of x is a constant on the interval. F of x is a constant. Is a constant on the interval. Okay, capital C. Okay, C is the first letter of constant. What it means is that for any input, the output is C. Okay, so the function will be like this, right? For any number, the output is a capital C. The same number for output for all the input. And then this function is, of course, a constant, is continuous differentiable. And at the end points, f of a equals to f of b, that also tells us that f of a is equals to f of b and equals to the constant. Okay, so under the circumstances, we will have f of x equals to the constant, and that constant is going to be f of a. F of a, and of course, it's also f of b. Right? As a constant, the derivative of the function is zero, right? It's zero. So the derivative of the function, is zero everywhere, right? And of course, we can take any c in between a and b. So c can be any number in the interval such that the derivative at that point is equal to zero, because f is differentiable at every point inside the interval. So that's case one. Case two. Case two, we are saying f of x is not constant. Okay, f of x is not a constant. What does that mean? F of x is not a constant. If f of x is not a constant, and we understand, then there should be a number, there's some number inside a and b that is larger than suppose there's one of the cases, right? So we suppose that for some, okay, so there is a number for some, for some x, okay, it's inside the interval. It's inside the interval AB. Okay. But it is, and that number is, suppose that number is some number, right? Is going to be larger than f of a. There must be one. There must be one. Okay, then you say it could be less than. That will be the third case. Okay, that will be the third case. So it is not a constant, i.e., this is not true, right? The case one is not true. If case one is not true, there must be a input x between a and b such that f of x is larger than f of a. Okay. According to extreme value theorem, okay, according to extreme value theorem, there's an absolute max, there's an absolute min, right? So there's absolute max and absolute min somewhere in the interval. And because there's one number larger than f of x, that larger than f of a, and f of a is the same f of b, right? So that maximum, okay, according to extreme value theorem, there exists a maximum maximum, okay, in the interval, this maximum must be larger than f of a and f of b, okay? And that number is going to be, that number exists according to extreme value theorem, so that number must be not a and not b, right? That number is going to be larger than f of a and f of b. And so such number must exist. Okay, they say, well, could this number not exist? Well, it's not possible. If that number does not exist, that means it's going to be a constant, right? It's going to be constant. So since we have 1x in that interval that's larger than the value of the function at the endpoints, therefore we must have a maximum at C such that f of C is the maximum, is the local maximum, or you can say absolute max, okay, is the maximum, and C is inside the interval. And then f is, remember, after the second condition is that f is differentiable, okay? Since f is differentiable inside the interval, according to Fermat theorem, right? So Fermat theorem would apply, okay? By Fermat theorem, since it's differentiable as C, and f as an extreme value theorem guarantees we have a maximum, and therefore the derivative of the function at the maximum must be 0. So according to Fermat theorem, by Fermat theorem. OREM. Okay. So here we use that the second case that's not a constant. If it's not a constant, then we have a value that's going to be larger than f of a and also larger than f of b, right? Then according to extreme value theorem, we have maximum exists, and that maximum must be inside between a and b. And according to Fermat theorem, then the derivative at that maximum must be 0. Okay, and case 3 is similar. Case 3, basically we assume that, well, if this is not true, it could be, it could be the other way, right? Either equal, greater, or less. So it could be the other way. In that case, if there are values between a and b, right, f of x is less than f of a, f of b, then we also know, according to extreme value theorem, there exists a minimum. There exists a minimum at a point, say, we can call it D, right? We can call it D. And D is also between A and B. It has to be inside. It has to be inside because the minimum is going to be smaller than the values of the function at the endpoints. So f of D is the minimum. F of D is the minimum. Right? And since f is differentiable on the interval, right? According to Fermat theorem, by Fermat theorem, once again, the derivative of the function at the point C, which is the minimum, is going to be 0. So this is the proof of Fermat theorem. Okay, and now let's illustrate. There's some very interesting pictures in the textbook to illustrate these three cases. All right, so let's illustrate the first case. The first case is it is a constant, right? So it could be a case that it is a constant. That's case number A, right? So we look at that picture. Okay, it's a constant, right? F of A is the same F of B, right? This is A, this is B, and F of A is the same as F of B. So it's a constant, the derivative is 0. So any point is okay. And any point in the interval would work. Case 1. All right. And the second case, right? Let's take a look at a second case. A second case is that we can have a function, right? And this function is smoothly and continuously. Okay, so let me get this picture to you. Okay, so you look at this picture, right? On this picture, you can see F of A and F of B are the same. Okay, so that's F of A. And that's F of B. So at the endpoints, the third condition is satisfied. They have the same value. Okay, hold on. This is what my drawing is not that. It's not that amazing. So let me redo this and redo this one. Okay, so this is F of A, and the red one is F of A. F of B, they're the same, and the function is continuous. And the two numbers at the endpoints are the same. And since it is not a constant, and we assume that there's a point that's larger than F of A and F of B, so that's the second case. That's the second case. And there must be a maximum. So at that point of maximum, that C must be between A and B. Okay, because we apply extreme value theorem. Excuse me. All right. All right. So that's the second case. That's the second case. And the third case, it could be, okay, then we have a minimum. We have a minimum, right? It could be something like that. Okay, so I'm gonna bring that picture to you. The third case, it could be something like that. Like this one, okay? There we go. Let me clear these previous drawing. Okay, so in the third case that F of A is F of B, they're the same height, right? And there's a number that's less than F of A and F of B. So, and there must be, the minimum must be less than F of A and F of B. According to extreme value theorem, the minimum does exist, right? So if the minimum exists, then the number is between A and B, and therefore there must be the C, is at the, at point C is a differentiable because the function is differentiable at every point in the interval, of course, is differentiable at C. According to Fermat theorem, that's case 3. Okay, the derivative will be 0. Could there be other cases? Absolutely. Okay, we talk about that on the way, it could be we have both. Okay, so let's have a discussion. Okay, there be other cases, certainly, right? Sometimes there's only the, the max, local max or local min. Well, format theorem, well, I'm sorry, extreme value theorem guarantee there will be, for continuous function on a closed interval, we will have max and min. But because, and sometimes we have, the max and or min, then you say where the minimum? Well, the minimum could happen at endpoints, right? The minimum could happen at endpoints. There could also be, in this case, right, f of a the same as f of b. We have both max and min, right? So in this case, we actually have 2c. Okay, we always have 2c. No, we can only guarantee we'll have 1c if all three conditions are satisfied. We cannot guarantee 2. So when in the statement of the theorem says there exists a c and that it guarantees there's at least 1c. Could there be more? Could be 7, 6. It's all possible. It's all possible. Because you can see if we have a continuous function from point A to point B, we can wiggle many times, right? So you could have totally many C's, but the theorem guarantees there's 1. Usually when we see this kind of language is that there's 1, then there's at least, that means there's at least 1. There are at least 1. Okay. Now, we did some let's try some of the homework questions. Let's apply Rolle theorem. Okay, so apply Rolle theorem. Okay, apply Rolle theorem. Apply Rolle theorem here. We're going to look at some homework questions. Okay, one of the homework questions I have selected. We did a number 12 in class, so maybe we do it again, right? Okay, so example number 1. Okay, so this example tells us to verify that the function satisfies the hypotheses of the Rolle theorem. No, actually, it's not number 12. Number 12 is using mean value theorem. We're going to do number 6. Okay, we did this in class, but we're going to do number 6. Number 7 and number 8. Okay, so verify the function satisfy the hypotheses of Rolle theorem. Okay, of the Rolle theorem. And then, okay, of course, on the given interval, and then find all the numbers C. Okay, all the numbers C that satisfies the conclusion of Rolle's theorem. Okay, we have Rolle theorem. There are 3 conditions, and let's look at number 6. Okay, so this function we have f of x equals to, we got x to the power of 3 minus 2x squared minus 4x plus 2. And the interval is from -2 to +2. It's a closed interval. When we are asked to do such things, we must verify condition after condition. So there are 3 conditions, right? There are 3 conditions that we're going to mention it. We're going to mention all of it, right? The solution, okay, this is how you should phrase the solution. Number 1, well, f is a polynomial. Polynomial is continuous everywhere, and certainly it is continuous on closed interval. So you can say f of x, okay, is continuous on the closed interval. Okay. Number 2 is polynomial is differentiable everywhere. Okay, and it's differentiable for as many times as you wish, right? So the function is differentiable in the interval of -2, 2. Okay, you just want to make sure it satisfies the Rolle theorem. So I'm going to copy and paste Rolle theorem and put it right underneath the work we are doing. Okay, so we can just do it. We can just compare, right? Number 3, and of course, at this point, okay, when you show your work, you can actually differentiate. Okay, so this way of showing work is slightly different from what I did in class. So you can take a derivative, that's 3 to the power of x squared minus 4x, right? Minus 4. Number 3, the third condition, which is f of a, f of b, and our a, so you're going to have to verify f of a here is negative f of -2. So you're going to plug in these numbers properly. Okay, so replace x by -2. Here, the parentheses must be present, because if you drop the parentheses, the first one is okay, but the second one, third one it will make a mistake. Okay. And evaluate. Okay, it's -6. I'm just using the software, and these calculations, you don't have to show the greatest details. Okay, and then f of 2, then we're going to plug in, okay, on the x is replaced by 2. So that's 2 multiply 2, put a dot there, and this also equals to -6. And better yet, if you would point out, right, f of -2 is the same as f of 2. Okay, that would be even better. Now you say, isn't that obvious? Yes, true. Okay, in a lot of cases, when you're showing mathematical work, you pointed out the most obvious to make your case. Excuse me. Okay, so all 3 conditions are satisfied, and that's how you demonstrate, right? You mention it even though it is so obvious, right? Because we want you to verify all 3 hypotheses are satisfied. And you're going to apply the conclusion, right? Then you say, by Rolle's theorem, there exists a C in AB, and A should be from -2 to +2, such that f of C, the derivative at C equals 0. Then, i.e., in our case, that is equals to 0 when x is replaced by c, because c is a number that we claim it exists, equals to 0. So next, we're going to solve for c. We're going to solve for c. Okay, so this c should be inside the interval, right? How do we solve for c? Well, solving quadratic equation, there are 3 ways, right? Quadratic, you can factor, quadratic formula, and you know, it really, you don't have to be limited, right? You can do factor, you can do quadratic formula, you can even do completing a square, right? If factoring seems to be like a little too much work, then you can totally just use quadratic formula. Okay, so I'm going to use quadratic formula here. So quadratic formula, c equals to, this is 2 times 3. And here we have a 4 plus minus square root, right? Square root. Negative 4 squared minus 4 times a, which is 3, times c, which is negative 4. Okay? And then what do we get? The inside the parentheses, we have 16 plus 48. I think that's a 64, right? And the denominator is a 6. And the square root of 64 is 8, right? So we have 8, right? I have 2 c's here. C1, c sub 1 equals to 4 minus 8, right? So that's going to be negative 2/3. Okay, so negative 4 over 6 is negative 2/3. C sub 2 is going to be 4 plus, that's going to be 2. So we got 2 c's. And now let's look at the statement in the theorem. The c we're looking for is in the interval, not at the endpoints. You see, in the interval, it doesn't include the endpoints. So even though we have another c found, that's 2, we really just have 1 c. Okay, so the c, okay, according to the by Rolle theorem, theorem is the C1 equals to negative 2/3. It's inside the interval between negative 2 and between negative 2 and positive 2, and that's the C. Okay, so now let's look at the interpretation. Oh, okay, so by this time you're finished. Okay, the question that we wanted to do is already done. But to illustrate this, oops, okay, to illustrate this, I would like to show you a little picture. Okay, and so the illustration. Okay, so here's the illustration between negative 2 and positive 2. So this is the curve of the function, right? So I'm going to make some adjustments. So it will just show mostly between negative 2 to positive 2. Okay, so negative 2 to positive 2. So the view would be from, so it's negative 2.1, and this is going to be 2.1, just a little bit. Right, so this is going to be negative 7, and this is going to be, say, 2. Okay, so the function where we see, it looks like I need a little bit higher. Okay, so 7. There we go. Maybe 5. 5 will be sufficient. Okay, so we'll make some adjustment. Okay, so at -2, okay, so let me change the number to the tick mark of the number to be simpler. So have -2 to +2, that's the closed interval. And f of 2, we have evaluated the value of the function, right? F of -2 is -6. F of 2 is -6, right? So these two values are the same. So we have 2 points. We have 2 points. Okay, we have 2 points, and these 2 points, one is -2, -6, right? That's one dot. And there's another dot, which is 2, -6. Okay, so let me use red dot. Okay, let me use red dot. Red. So these are the 2 red dots. So we can see at an f of 2, right? So let's draw some vertical line. I'm going to draw some vertical line to illustrate to you. So -2, 0, you don't have to know how to use this software. Okay, that's one vertical line. Okay, make it thicker with the medium. And the next one, there we go, so +2. So these are the two, f of A equals to f of B, right? F of -2 is the same as f of 2. Let me mark it. I'll mark it a little later. Okay, just mark it a little later. So, and the point C is -2/3. Okay, so what is the function's value? Right? So that point C is in between. Let me use the what color? Let's see, use a purple. Okay, I'm going to use purple color. So that point is -2/3. But what is the value of the function at -2/3? Well, that's going to be the value of the function. And the tangent line, right? The tangent line at this point. So we're going to draw. We were not asked to find the tangent line because the tangent line is a horizontal line anyway, right? So we're gonna do a complete illustration here. So f of x that equals to so let's evaluate f of x at a -2/3. Okay, -2/3. Okay, so we're going to plug in this number at -2/3. So we let the computer do the work. Okay, so what do we get? So it's 94/20. You don't really need this number, but we just want to plot that point to know how high it is, right? So we have -2/3. And -2/3. And what is it? I forgot the number. I have to go back. Okay, I have to go back. Okay, I'm going to go back to find 94/27. 94/27. Okay, so 94/27. 94/27. So this way we can draw a purple line there, right? So this point, okay, this point, if I want to put a purple dot there, okay, if I want to put a purple dot, that purple dot would be this. That's purple dot. So that's the point C where the derivative, okay, the derivative of the function is 0. And the tangent line, let's draw the tangent line. Okay, the tangent line, of course, is 94 over 27. Okay, that's the tangent line. And this tangent line is parallel to the line connecting the two endpoints. Okay, this is -2. This is -2, -6, and this is a positive 2, -6. So I'm going to draw that tangent line. Then I'm going to mark some points for you. Okay. So from -2, -6. So this tangent line and this is secant line, they're parallel. So this line is the tangent line passing points at C of the function. So let's do some markings of these points so you guys have some relevance, right? So understand what is what. I hope this helps, okay? If you guys are not bored. So the red one, okay, the red one, this is the f of -2, okay? And this red one is f of 2, okay? That, of course, equals to -6. That equals -6, f of 2, they're the same. And this is the horizontal line connecting the two dots. So this point is -2, -6. Okay, this is A and this is f of A. Okay, which is A f of A. Okay, understand these notations. And this piece is 2, 6. Okay, which is B f of B. Okay, so connecting the two endpoints, and that line, of course, is horizontal, and the tangent line passing this, at the tangent line to the curve at C, which is this piece, and that tangent line is which is equals to f of C, which in our case is 94 over 27. This is the tangent line at C, and the point C is, okay, in our case, that's C, f of C, which is in our case, -2/3, 94 over 27. Okay, so this is the complete picture. Let's see if I have missed anything. And the derivative, of course, the derivative of the function, okay? Derivative of the function at a -2/3 is 0. That's f of C, the derivative at C. You see all these relevance, how they're reflected in the picture in this particular example. Okay, in this particular example. And in this question, we were not asked to find f of C. So you don't need to find f of C, but you should know how to find f of C. F of C is a point on the curve, right? So the endpoints, all these points are being marked. So that's the whole of the picture. If you have any questions, please don't hesitate. I think I don't want to make this lesson too long. Maybe in another lesson. And here I wish to talk about another example which we did in class. Even though we did it in class, I just want to make sure you guys understand it. And then we're going to close this lesson. Because we don't want to make it too long. Okay. All right. So the second example is also on your homework. Okay. The second one is on your homework. And what this one says, let the function, so I'm going to call this example number 2. Okay. This is homework number 9. f of x is equal to 1 minus x raised to the power of 2/3. Okay, let me make the funds a bit larger. 250%. Okay. And the interest in the interval of interest, okay, show that f of -1 is the same as f of 1. We're going to show that, but there is not number C inside the interval from -1 to +1 such that the derivative of that function of the function as C is 0. Such number does not exist. And then the question is, why does this not contradict Rolle theorem? Rolle theorem says if all 3 conditions are satisfied, okay, and here we first asked to show f of -1 equals to f of 1. But in our mind, you need to think about there's 3 conditions. There's 3 conditions. Only after all 3 conditions are satisfied, then we can say the conclusion would apply. If one of the conditions doesn't satisfy, right? So suppose that we have this all 3 conditions banded together, right? All 3 conditions. So if, right, all 3 conditions, we're going to have 3 conditions. Oh, never mind. So I'm going to do all 3. Okay, so my intention is to show you the logical relationship. Okay, the first condition is continuous on that. Let me just be patient. If, right, the first condition, the second condition, right, so I have to do it anyway. So differentiable, all 3. Okay, the third condition is f of a equals f of b. Okay, I want to show you clearly the logical relationship. Okay, if all 3 are satisfied, then the conclusion, right? We have that conclusion. I'm going to put the conclusion in the box. Okay, so if this big box, let's see if I can make it. Okay, if the first box, then this is the logic we have talked about, right? If A, then B, right? If the first big box, then the second box, right? That's A and that's B. And if not B, if that is true, if not B, then what? Then not A. Okay? If this is true, then if not B, then not A. Now, let's see, what kind of situation do we have here? Okay, what kind of situation do we have here? Okay, so see if it contradicts to the theorem, right? So we have that clear logical relationship with us. Okay, so I'm going to make this dark. Let's make this dark. Now, so let's do the question, f of -1. So let's see what this function is. Okay, this function basically is 1 minus cubic root and x squared. That's the function we're dealing with. Okay. F of -1 is 1 minus, should we just plug in? Okay, replace x by -1. And of course, the answer is 0. Wait, we have an extra one, sorry. Okay, so from here, we get a positive 1. So 1 minus 1 is 0, right? What is f of 1? For f of 1, we're going to plug in the 1. Then we do this all over again, right? So this is 1. So we're going to get 1 more time. So that part is verified. Okay. So we are asked to show this piece that is verified, right? Verified. This is to say that if we look at the interval between -1 to +1, f of -1 is the same as f of 1. The third condition is satisfied. The third condition, the condition of f of A equals to f of B in Rolle theorem is satisfied. Right? Should we just go ahead without verifying the other two conditions? Maybe not, right? So we should also try to look at the other two conditions. Continuity is no problem. Okay, f is continuous, and this function is continuous on the closed interval. So f is continuous. Okay, the third condition is satisfied. The first condition is also satisfied. So f is continuous on this interval between -1 to +1. Okay, that's guaranteed by the result we have learned before. Okay, about continuity. Now the question is, can we take a derivative? Is it differentiable? Right? If it is differentiable, we can take a derivative. We take a derivative, and what do we get? The derivative of 1 is 0. So derivative of negative x to the power, 2/3 is going to be negative. This is going to be negative 2/3. X raised to the power of 2/3 minus 1, right? And that equals to negative 2/3 x raised to the power of negative 1/3. And what function is this? This is a negative 1/3, negative 2/3, sorry. Multiply, if we write it in a familiar form, it's going to be cubic root of x. X is in the denominator, and in this case, the domain of the derivative x cannot be 0. X cannot be 0. In other words, right? If you try to find C, if we try to find the C in the theorem, what do we have? We're going to set this equal to 0, right? So we're going to set the derivative equals to 0. We can save all of these. We set it equal to 0. Assume that C can be found. But when we solve this equation, right, denominator cannot be 0. That's determined by the domain. And then this will never be 0. There's no solution. So the C does not exist. Does not exist. Does this contradict with the Rolle theorem? No, because here we already see that 0, which is inside the interval between -1 to 1, at this point, the function is not differentiable. Okay. F of x is not differentiable at 0. If f is not differentiable at 0, thus f is not differentiable in the interval between, excuse me, -1 to +1. Because when we say a function is differentiable on an interval, it is differentiable at every point in the interval. And now there's one point, the function is not differentiable. So we cannot say f is differentiable in that interval, i.e. that f is not differentiable. So that's why that Rolle theorem, not all the conditions are satisfied, right? So there's no C that tells us that one of the conditions is not satisfied. Not B, then not A. But A has 3 conditions, right? A has 3 conditions. So it could be one of them. This number 3 works, number 1 works, but number 2 doesn't. That's why it doesn't contradict with the Rolle theorem, because Rolle theorem didn't say you can remove the second condition, right? If we recall how important that differentiability is in the proof, the second condition is very important because that's when we can apply the Fermat theorem. All right, so this is the second example we have covered today. And for other examples, I think I will save it for another time because I really don't want to make this too long. Thank you for watching. This is basically what we covered in class. If it's too much, if it's repeated for you, then you have a note, but hopefully, this will help. Thank you. Thank you for watching.